Sì.
Okay, so we
So you prefer H and K than J? J can be sacrificed at some point.
Supongo que me sé el día. Pero sí, no sé. Lo dices tú mismo, si quieres. No sé qué es más fácil. Porque no se puede pintar. Yo no se puede pintar las alarmas. Por orden del capitán de fragata. No tiene suerte. Por orden de la autoridad, no se puede.
Las notas son 20 minutos.
Sí.
¿Te parece bien si te hago un warning a los 15? A lo mejor
Sí.
no me levanto.
Creo que iré bien de tiempo, creo. O sea, que no hay problemas. Pero sí. Sí.
Después de los 15 quedan
Sí,
un
para
par de
estar un poco
minutos
tanto, sí.
más.
Sí. Es el Sherman efecto, ¿no? De todas las sesiones.
Y por alguna razón me saqué siempre todas las fotos.
¿Sí?
Sí,
Pero no estabas.
que no me había enterado. No, tuve que volver al hotel por una telecom después del almuerzo ayer. Entonces esta cuando se cogió.
Diría que fue la tarde. No, fue justo antes del mediodía. Al fin. Ah, no, fue por la tarde. Fue en el break de la tarde, sí, porque están los de la industria que hicieron la mesa redonda por la tarde. Sí.
Bueno, a lo mejor podríamos hacer una versión donde le pegamos mi foto.
Poca gente el viernes a primera hora.
Good morning. Okay, so we start with the session. Please take your seats. Okay, so good morning, everybody. We start the last day of the meeting. This session is the request for simulations for Gaia NIR infrared. So the first speaker will be Edward Massana with the Gaia NIR infrared simulator, a BGM. Just before we start, a small announcement. Apparently today the meeting room in the second floor is off limits. We are not allowed to use it. Okay, sorry about that.
Okay, good morning, everybody. Okay, I will tell you about the Gaia NIR simulator and in particular the use of Besançon Galaxy model. Cierto. ¿Cómo? ¿Cómo comparto? Sí, ya, claro, pero... pero no lo encuentro. Fes-ho tu, sisplau. Vale, que està aquí, sí. Ara, sí. So, good morning again. I will tell you about Gaia NIR a simulator and in particular the use of the Besançon Galaxy model. By the moment, the goal of the simulation for Gaia NIR is to get a realistic estimation of the number of sources observed by Gaia NIR, including the spatial distribution, motion, physical characteristics, etc. In the future, we probably need a more specific simulations for telemetry, even for pixel level. But to do this, we will need a well-defined model for the instruments that we don't have yet. So by the moment, we focus in this estimation of the number of sources. In any way, this can help, for instance, to define the final instrument characteristics, to modify or improve the observing strategy, or to determine the telemetry budget. Of course, to do this, we can start from some work already done some years ago, that is the Gaia simulator. Gaia simulator was a code, a very big code, structured in several modules to cover all the needs needed by the mission. In particular, we have 3 different simulators, one for the telemetry, one for pixel level for image, and one for the main database and universe model simulation. Part of these modules, in particular these 3 parts, can be really used for Gaia NIR. In particular, the Gaia object generator, GOG, that was a tool or is a tool designed to simulate the catalog, can be used for Gaia NIR. All the data generated by GOG is based in so-called GUMS, the Gaia Universe Model Simulator. This model provides the astronomical sources to be observed with the position, kinematics, magnitude, physical parameters, etc. And it has different components. In particular, we have stars in the Milky Way based on the Benson galaxy model, but also LMC, SMC, extragalactic objects, solar system objects, etc. Benson galaxy model, BGM, is a global view of the galaxy, including dynamical and evolutionary aspects. From a scenario of the formation and evolution, the model provides theoretical distribution for photometry, kinematics, abundances, etc. The first version of the model is from more than 20 years ago, but since then, substantial change have been performed to improve BGM. All the information is described in the webpage of the model here. And in particular, in this webpage, you can find the different characteristics of each component of the model, the bar, the thick disk, halo, thin disk, which extinction model are included in the BGM, also the photometric systems available for producing the catalogs, kinematics, etc. So if you want, you can go to this webpage for more information. Now I will show you a couple of applications of BGM to Gaia NIR. The first one is the computation of stellar densities equivalent to G21 magnitude for 3 different directions. To the galactic pole, to the galactic anticenter, and to the galactic center. The simulation was done for several filters, from the first here, from 200 to 1,600 nanometers, up to the filter that now is adopted at the filter for the astrometry field of view, from 800 nanometers to 2,400 nanometers. In the direction of the galactic pole, the density is around 4,000 stars per square degree. At the anticenter direction, it's around 200,000 stars per square degree, and in the direction of the galactic center, the density can reach up to 10 million of stars per square degree. We can also compare these numbers with the Gaia numbers and take a look to the variation with the galactic longitude and latitude. here the more important number or figure here is this one that at the galactic center we can reach up to almost 40 times the stars observed by Gaia. In the future, maybe in the next future, we want to run a new set of simulation focused now just in the N-band, using the latest version of BGM with some improvement, in particular the extinction model, and study the possibility to do all-sky simulation. But maybe, probably, is out of the current CPU resources. If you take into account that for Gaia we need some hundreds of thousands CPU hours, for Gaia NIR, if we use the same structure, probably is out of our possibilities. Other application of the Besançon Galaxy model to Gaia NIR is to evaluate the distance limits at which stars can be observed by Gaia NIR. We apply this methodology to red clam stars, but it could be applied to other populations. We start the key part of this methodology is the extinction model. In this case, we use BGM with a combination, depending on the distance, of L'Allemande and Marshall models. Here on the left, you can see the extinction on the galactic plane. Note, for instance, that in the N-band, at the direction of the galactic center, we have around 4 magnitudes, compared with more than 10 magnitudes in the G-band. And on the right side, this is a vertical cut of the extinction. The way to obtain the maximum observable distance is just using this relation between apparent absolute magnitude, distance, and absorption. To do this, we adopt as the apparent magnitude the limiting magnitude in G-band and in N-band, 20.7 for G, 24 N, and also you need to assume a characteristic or mean absolute magnitude for the population. In this case, for the red clam stars, we use these values here, 0.44 and -1.1. The blue line here shows the maximum distance that Gaia can observe the red clam star, compared with Gaia NIR in the red line. For instance, in the direction of the galactic center, with Gaia NIR, we can observe beyond 20 kiloparsecs, when Gaia stops around 8-10 kiloparsecs. And the same for the vertical cut. At high galactic latitude, you can observe, obviously, further. We can also study how the limiting magnitude affects this maximum distance. In blue is N20, in orange N21, and in green N22. If the extinction model is correct, of course, for instance, in the case of N22, we can observe up to more beyond 50 kiloparsecs in the direction of the galactic center. And finally, we can also estimate the number of stars in a given direction. To do this, we need, from the Besançon Galaxy model, a density profile, and just integrating this expression, we can get the numbers, in this case, of red clamp stars, as the map shows here, and also compare with Gaia, when we can see that at some areas of the sky, we will observe up to 10 times more red clamp stars with Gaia NIR than with Gaia. But Besançon galaxy model is not the only way to estimate densities. I will show you now a couple of other methodology. The first one is the Gaia mock catalog developed by Marie. The idea here is to convert any simulation in a Gaia NIR-like catalog. So our input is a simulation with the needed parameters, and then from this we add the Gaia observables, so we transform to Gaia or Gaia NIR magnitudes, we add the Gaia or Gaia NIR uncertainties, use a extinction model, and as output we get a mock catalog with the same characteristics of the Gaia catalog or the Gaia NIR catalog. This code is available at the GitHub in the bottom corner here. Other methodology is to use surveys already done. For instance, for the large Magellanic Cloud, we can use the SMICE survey and compare the observations from Gaia or from Gaia NIR with this survey. Here I show you some numbers for a small relation around the LMC center, when we can see that if we observe in n up to 22 magnitude, we will observe 75% of the SMICE survey. And finally, I will show you other methodology, that is this simulating particles with the Koshimoto model. Koshimoto, it's a model developed for microlensing studies. It is based on the VVV survey plus Gaia. It has several components, 7 for the thin disk, 1 component for the thick disk, the bar, the NSD, the NSC, and of course also an extinction law. This work was done by Pau, the next speaker, and he studied a very small area around the galactic center with a very, very high density, around 27 million stars per square degree, and they compared the model with Sirius, a survey of the galactic center, and as you can see here in the histogram, the survey is almost complete up to 12, 13 magnitude, and from here, for fainter stars, is not complete. This means that we are, from magnitude around 13, we are losing stars due to the confusion, to the blending. In the diagram on the right top left, the horizontal axis is the angular separation between the stars. The vertical axis is the difference in magnitude, and both vertical lines are the angular resolution for Gaia NIR large and medium design. In this diagram, stars at the bottom left corner are stars hard to detect because they are very close and with a very large magnitude difference, and the stars on the right side, in particular on the top corner, are stars easy to detect because they are well separated and with a small magnitude difference. the important thing here is that there are very few stars on the left of the vertical line. So there are very few stars hard to detect. This means that blending is not an issue for either Gaia NIR medium or Gaia NIR large. The real limitation is the number of stars, the crowding, because we will have too many stars to be observed and to be downloaded. We can also study how the variation on the limiting magnitude affect the different components of the model. Here, the histograms are for N17, 16, 15, and 14. And as you can see, when we reduce the limiting magnitude, the components more affected are the bar and the NSD and NSC. And the summary here, we will need a realistic estimation for the number of sources observed by Gaia NIR to help on the design of the instrument, the improving of the strategies, etc. We can start from Gaia NIR simulator and in particular from the Besançon Galaxy model, but there are other tools that we can use, as the Gaia Mode catalog, studies of completeness, simulating particles from model, etc. That's all. Thank you.
Thank you. Questions? David Dobbs?
Hi, thanks. This is a very useful work. It's really important, actually, because it's the thing I get asked the most, basically. You know, what's the crowding and how many stars we can observe. Could you go back to this table you had near the very start with the old number counts? It's an older table, I think. But
this one. Yeah. This is very old. But
yes,
okay.
Sure, yeah. So I mean, you have many variants here where you do calculations. You don't need to do all of these anymore because we've more or less fixed now to Gaia NIR 23 instead of 24. So yeah. That's the variant that we have in the design now, and we should just do that simulation and avoid having to do all the others. But we do want to go. We do want to get it for G. This is G equals 21. We want it for G 21. Equals 22 and 23 also. Yeah, which you're doing, I think, in the later plots.
Well, this presentation is more for the methodology, but for the numbers. In particular, this one is very old, as you say. It was the first attempt to get some numbers. So, in such a way, forget the numbers, because you are right. We need still to change a lot of things. This is why we are now planning to do some new simulations. Yeah. So this is an estimation. As you know, even this 10 millions is between 10 and 70 millions. So something in between. No?
Yeah. Okay. Yeah. But remember, it's 23 instead of 24.
Yeah. Sure.
Thanks very much.
We will check with you all before to start.
Sure. Yeah. Just so we don't waste time.
Jordi.
You mentioned all the huge amount of work that has been done in GAS, GVs, GOG, and so on. I know that there's a huge amount of work there. If we want to reuse all of these, which makes complete sense to me, does it mean that we are stuck with Java to simulate all of these? I guess so.
My personal opinion is that we should not reuse the code as it is, because now it's a very big code, very complicated, very difficult to maintain, to modify. So I think that we can, of course, maintain the structure, maintain the philosophy, but probably it will be easy, no start from scratch, but maybe think a little bit before.
Or pass everything to ChatGPT and convert to...
Yeah.
Okay, thank you.
In any case, I have to say the Java works very well for the simulator. Yeah.
Okay, thank you. I think we need to move on. Let's thank the speaker again. So the next talk will be given online by Pau Ramos about the Jasmine astrometric flexible block iterative solver. How do we share? Okay. And Pau, can you hear us?
You have to unmute.
Yes, I can hear you.
Perfect. Okay, so then the floor is yours. Then the slot is 20 minutes, so I guess we're aiming for 15 plus 5, more or less. Go ahead.
Got it. So, hi everyone, my name is Pau Ramos. Some of you already know me, but for those that don't, I'm currently a postdoc at the National Astronomical Observatory of Japan, and I'm working on the data processing pipeline of the Jasmine mission. And you might be wondering, who is this Jasmine? So basically, Jasmine is the upcoming Japanese high-precision near-infrared astrometric space mission that will also provide excellent photometry and high-cadence light curves for the variable sources. While small, is only going to be 32 centimeters telescope, we can still do a lot of science with the bright stars. So it has two main scientific goals. On one hand, discovering and characterizing exoplanets around M dwarfs, and on the other, the creation of an astrometric catalog for the bright sources in the galactic center that allows us to study the dynamics of the innermost parts of the Milky Way. As you may recall from Francisco's talk, in this region, deeply obscured and reddened by the dense dust, coexist the galactic bar, the nuclear stellar disk, and the nuclear star cluster, whose origins and formation mechanisms are not yet completely well understood. So, to analyze the kinematics of these stars, we need high-quality proper motions. Moreover, we also want to join the Jasmine parallaxes with the prime photometry to do a careful calibration of the luminosity relation for the miras that we find along the line of sight. So, to achieve the scientific goals, we have some strict requirements on the astrometry precision that we need to reach for these stars in this region. So now the question is, how do we get global astrometry for this relatively local area that contains mostly stars that are very far from the sun? Well, there are many pieces in the data processing of Jasmine, but today I will be covering only this last part that has to do with the astrometric solvers. The key idea is that after properly self-calibrating the instrument, we can obtain the positions, parallaxes, and proper motions of the stars, well, of each star, with respect to our reference Gaia stars that will act in this context as anchors to the ICRS. Just to give you a funny number, if we were to do this the old-fashioned way, we would have to sit and process 1 million astrometric plates, which together they would weigh above 300 tons. Just to give you an idea of the volume of data that we're dealing with in Jasmine. But before we can even consider estimating any astrometry, we need a model. We need a function that tells us the path that the photons took from the star as they travel through the solar system into the telescope, they bounce around in the mirrors, and they hit the detector at a set of coordinates that I will refer to as kappa and mu. So for those of you that were here yesterday, you will remember Gabriel's talk where he explained some pieces of this model in great detail. However, what happens if the star is not where we think it is, or if the telescope is not pointing exactly where we think it is pointing? Well, the importance of this model is that it allows us to understand how the position of a source on the detector changes when we modify the parameters of the star or the orientation of the satellite. To be a little bit more precise, we can have a good guess of where the star will appear on our detector. Sorry about the arrow. On our detector, basically by applying our current best available knowledge to our function. And that's going to give us an initial guess using this initial set of parameters. We can also perturb this prediction using the linear terms of the Taylor expansion, which you can see here. But if we put this in a matrix form, we obtain this equation where the observations, it's obviously the observations for all the stars. This f of p is the current best prediction that we have. And then what we want to do is equate this to the design matrix. This is this D and contains all the derivatives, and to delta p, which is the small perturbation. And from now on, I will refer to delta p as updates, because at the end of the day, what we want to do is find the updates that minimize the new residuals. And to do that, we are going to be using least squares. So in summary, we linearize the problem, we take an initial guess, we compute the residuals and the Jacobian at that initial guess, and then we solve via least squares. Very important note here, whenever we are computing Jacobians, that means that we have, normally this is how it would work, you would have to derive by hand all the derivatives of your model so that you can write them down on your software. So if you change your model, which is going to be the key, the main motive of this talk, you introduce new parameters, you change a function, whatever, you have to re-derive all your derivatives so that you can code them. Let's put a pin on that for a second and let's focus on the design matrix, this D matrix here. As you can see, for the case of Jasmine, we are going to have a huge matrix. It's going to be 10 to the 10 rows, which correspond to the observations, and 10 to the 7 columns. And in this case, its source will contribute 5 columns to the matrix, or 6 if we do as in Gaia, and we include a color term as well. So the most simplest way to solve this problem is by direct inversion. So inverting the matrix D here. However, for a matrix of this size, this turns out to be extremely difficult to do. Luckily, it turns out that for Jasmine, it is just barely possible, as the ARI team in Heidelberg has demonstrated with their software called AJAS. In AJAS, they actually are not inverting the design matrix, but what they do is they go to the normal equations and then they do some forward elimination to create a very dense 1 million by 1 million matrix that is then it's just small enough that it can squeeze all the information into a decent sized cluster and solve it via the pseudo inverse. The advantages of this method is that it gives us the full covariance matrix and the spectra of our solution, so we can really analyze our model and study the degeneracies that it has. The problem is that it cannot deal with missions much bigger than Jasmine, so that's a little bit of a trade-off. So in contrast, the traditional approach that is also used in Gaia exploits the very big sparsity of this matrix. So what we do is we break the design matrix into different blocks such that each block contains independent sets of observations. This is for the attitude, but this would be for the calibration, for instance. It is just an example. Then what we do is we simply solve each block independently, and because they are independent, we can fully parallelize this process. And after a few iterations of going through block, and then repeat, the correlations enter through this iteration process, and they are propagated, and the system can reach the final optimal solution. So, sorry, let me go back 1 second. So the main advantage is that we can solve more complex problems. We are not so limited to the size of the problem, but of course, we don't have the full covariance matrix, so we lose some information. Damn it, I'm sorry. Okay, so this is the approach that we took when we were designing and implementing JAXBIS, which is the name that we have given to the Japanese side of the processing pipeline of Jasmine. So when designing JAXBIS, we had 3 goals in mind. On one hand, we want to establish the state-of-the-art of astrometric solvers. On the other hand, we want to create a software that is very flexible so that many different surveys, missions, and teams can use it, but without compromising the performance. And most importantly, what we are trying here is to build a framework into which we can quickly test and develop our calibrations models. And I cannot stress this enough. but finding the right calibration model for your instrument and your survey is mandatory to derive good astrometry. It basically becomes the main challenge for whenever you are designing an astrometric mission like Gaia NIR. To give you an example with Jasmine, what you can see is that the histogram of the color of the sources that Jasmine will observe is very bimodal. On one hand, we have the very blue sources, all of which have really good Gaia astrometry already. And on the other side, we have the red giants that are also reddened, which are our main scientific target. So the challenge becomes how to do this correctly, for which in the case of Jasmine, we will really need a good understanding of chromaticity, among other effects, in order to meet our targets. Generally, how it goes is that you choose a calibration model, you run your solver as fast as possible, and then you spend a lot of time analyzing the solution so that you can come up with a better calibration model, doing it like this, and then you just continue to iterate this process until you're happy, basically. So the idea here, the goal is to create a framework such that we can dedicate all our time and resources to analyzing the residuals and coming up with new models, instead of having to rederive the derivatives. And this is a key thing, because ideally what I would like is the solver to run instantaneously. And when I update the model, I would like to just change one line of code in my software, and then I can run it again. That's what we are aiming for. And just as a fun fact, this is how James Bradley discovered the stellar aberration in the 18th century, on this step. This is where the interesting stuff happens, not on the other ones. So let's try to get them out of the way. But how do we do that? Well, the answer that we came up with here at NAOJ is using JAX. JAX is a Python library for high-performance computation and a major framework of differential programming. And I will be talking more about that in a second. For now, let me walk you through how JASBIS works. Here on the right, you have the observations, which corresponds to the position in the detector of each source observed at each exposure. When we compare it with our initial prediction, we get basically the initial set of residuals. And for that, we are using the vector mapping and the just-in-time compilation functionality of JAX to accelerate this process. Then we need to calculate for each observation the derivatives of the model with respect to each of the blocks that I have defined before. And here is the main novelty that we are introducing, which is using the auto-differentiation power of JAX to calculate the derivatives without having to derive them by hand. So in this sense, JAX will trace the variables through our model function and apply the chain rule to obtain numerically exact derivatives without the need of us getting involved in the list. So when we combine this with the vector mapping and the just-in-time compilation, this results in very fast times of computing the derivatives. And with this design, we only have to look at the observation once, but we still need to compute the Jacobians many times. So we need to be really fast in this sense. To do all of this, we need to be constantly reading and rewriting the residuals array. Therefore, the obvious solution is to keep them in RAM memory. However, in the case of Jasmine, we are talking about roughly 500 gigabytes. Therefore, the trick that we came up with is to use a subset of the nodes of the cluster just to hold the residuals in memory and to make sure that each processing node is receiving the right portion of the residuals at the right time. And we are calling this the remote RAM server because it acts as a servant, and then the rest of the cluster will act as a client. Just to give you a quick example, if I have time, basically, let's suppose that we are updating the source block, no? And then we have the worker one is going to be trying to update source number one. And to do that, it has to pull from the node that contains the residuals for source one, which is the first one. Then we have worker 10 trying to update source number 10. And for that, it has to request to the last node that it provides the residuals for that source. After they are done updating, they have to put it back where they came from. Okay, it's all fine and well, but the problem is that when we move to the next block and now we are updating the attitude, it turns out that the access pattern is completely different. Why? Well, it just so happens that in this case, the first and the 10th source have been observed on the exposure that worker 8 is now trying to update. Therefore, worker 8 needs to call a portion of those residuals from both the first and the last remote RAM server nodes. And of course, this is more complex because we have many nodes working, we have many exposures, many sources. So you can imagine how complex this can get. Luckily, the Raccoons library that is being developed by Konstantin at ARI in Heidelberg helps us deal with all of these complications in a very efficient manner. And just a quick note here, whenever we're dealing with astrometric problems, this is a memory limited problem. And this fact, by necessity, has a big impact on the way the solver is designed. Just before finishing, let me tell you a little bit about the pros and cons of using JAX. JAX is very flexible. It's also written in Python, which means that it will be very easy for other people and teams to adopt and improve upon. And also, if used correctly, we are really not sacrificing performance that much. The main issue here is that it's really hard to manage the memory that JAX is using during the auto-differentiation. And therefore, it's hard to truly optimize the performance for one mission and one hardware. But still, we believe that based on the test that we have done, it's performant enough that it offsets the negatives. The goods win over the negatives. Just a quick update on where we are at with the Jasmine solver. So AJAS, which is the solver that the Heidelberg team is doing, this direct solver, has already been shown that it can deal with the full Jasmine mission in just 10 hours in a normal cluster. This is no Mare Nostrum. In Mare Nostrum, we would do it in like 1 or 2 hours. JAX-BIS is now currently being tested in this kind of high-performance computing systems, and it seems to be on par with AJAS in terms of performance. But we still need to optimize it, so we might actually be a little bit faster. We still need to test it. The main advantage that we have with JAX-BIS is that because we are using JAX, we can consider a deluxe approach to the optical and detector calibrations. And for those of you that don't know what deluxe is, I really recommend you that you check their GitHub page. It's very clearly explained, a lot of examples, and I think they are doing something very interesting here. These are mostly people from the Tollyman mission. I really encourage you to check it out. So let me finish. I'm not sure if I'm on time or not. Well, basically, take-home message. What I'm trying to say is that an AJAS-like direct solver could be used for Gaia NIR for the core solution, and then something like JAX-BIS with this philosophy could be used to make really quick development on the calibration model, and even probably with the future clusters, it should be able to be fast enough for the global solution. And also, once we get the astrometric solution for Jasmine, this will provide a very needed initial guess for the near-infrared sources that Gaia will be looking at the anti-center, along with many other missions that are also interested in that region. And that's it. Thank you very much. I will be happy to take any questions.
Thank you, Pau. Are there questions in the room or online? Yes.
Hola, Pau. We are still impressed, shocked by the way that you have made the presentation. Congratulations. I must answer. I must ask. At the very beginning, you said that there were 2 science topics, and one was exoplanets around M dwarfs. Can you please something about that?
Yes, of course, no problem. I'm not an expert, so I might say I don't know all the details, but basically the idea is because we are looking in the infrared, we can go and look at stars orbiting, we are targeting Earth-like stars, planets orbiting M dwarfs, because there the transit signal is very deep and they are relatively easy to detect. But also the other idea is to pierce through the dust in protoplanetary disks and try to look for the youngest planets as well. And I know that the team that is doing that, they have a lot of experience using in exoplanets, and they actually have developed a tool that is called ExoJax, in case you're interested. So Yeah, it's mostly going to be through the photometry, although probably the astrometry, if we manage to get a background source that we can use as reference, we could also use the astrometry to detect some planetary, some motion of the star due to the planets.
Thank you.
I guess what I forgot to mention is that this survey is happening whenever we cannot observe the galactic center. So the galactic center is a set survey, and we will observe it following a schedule. And then in summer and in winter, we cannot observe the galactic center, and the exoplanet teams has a list of planets that they want to target.
Okay. Is there another question? I cannot see hands raised in the room online. Do we have any question? Doesn't look like. Okay, perfect. So then we thank Pau again. Thanks for the very nice talk. So the next speaker is going to be Borcan Guiano, discussing the Halavambre surveys.
Well, okay, thanks. Good morning, everyone. Well, thanks for organizing this conference, and thanks for giving me the opportunity to tell you more about what we are doing in Halavambre, which I think is very, very exciting. What I'm going to discuss here is just like the goal of my talk is just to not only to tell you what we are doing in Cefca and in Halavambre with all the facilities we have there, also is just to see, okay, I got that. The host spotlight your video, I don't know, later, okay. Only just to see what are the synergies between Gaia NIR and what we are doing there. As I commented here, instrumentation is not going to be alone the challenges and the breakthrough for Gaia NIR. It's also how we are going to handle the massive data that we are going to collect, and we are going to transform this massive data into the resources for the science development that we need to do with the data we are collecting. Okay, so Halavambre, we are just leading what we have called the J+ and the J+ surveys. Okay, so we have already gathered thousands of square degrees. We know how to treat the data, we know how to collect the data, and we know how to produce the survey products and value-added catalogs useful for the community and to develop your science. By when Gaia NIR will be happening, J+ will be already complete, and we will have optical spectrophotometry for hundreds of millions of stars down to the 22 magnitude in the Earth. So I think the synergies between Gaia NIR and Halavambre facilities are just obvious. Okay, let me tell you a little bit more about where we are. So it looks like Teruel exists. We do exist. We are there. And so this is a little bit the facilities we have. This is the map where we are, just in case you are wondering. And so we have the observatory, we have the Hercules in Plaza San Juan, and we also have an outstanding astronomy outreach and training center called Galactica. We do need to transfer our knowledge to the society, okay? So we need to pay attention with that. I also want to mention that PLD Space is a company is also operating in the airport in Teruel, and also they have some infrastructure there. So we have a connection with the space already established in Teruel. Okay, let me tell you a little bit more about Halavambre. Okay, so we got the ticket of Infraestructura Científica Técnica Singular, which is just a target that we're just outstanding facility in Halavambre. As you see that we have two main telescopes. There are more telescopes and there are more facilities coming, but those are the original ones. We have the 80 centimeters one and the 2.5 meters. And I'm going to describe a little bit the kind of surveys that we are doing. So this is the small telescope. As you can see, these telescopes, they have been just developed to have a big field of view. And here the small telescope is just operating in 12 bands. And the main The main goal of this telescope is just what we call it the J+, the J+ survey that has been already collecting data for several years and the data release. The biggest telescope you have here, the first slide with M31, this is a big field of view, and this is the 56 narrow bands where we are just collecting the survey called J+. This started like a little less than 2 years ago, and just we keep going for the next years, just developing these surveys. Okay. Together with the big surveys, we also have been offering open time. Here I focus on the 80 centimeters, but now we have started to offer open time with the biggest telescope. So inside these big surveys, there are other small surveys that they are just using these facilities with different scientific goals. Okay? And this is open to the community. Everyone who is interested on the facilities, they can apply for telescope time here and just explore your ideas. This is the current status of the surveys we are doing. This is J+. J+ DR4 just was released last November. J+ started less than 2 years ago. And here you have those, in the top and in the bottom, you have the same targets that you can see where the filters and the information that they are giving you. So we are doing photometry, but thanks to the narrow bands, at the end, what you have is a low resolution spectra, and as you can see, they have been selected and optimized to be in the key feature, in the key absorption lines or in the key emission lines, where the information of the astrophysical objects are. Okay. We do release the data. Okay. So periodically, we have our philosophy is that we get the data, but eventually we will offer the data to everyone. Okay, this is something that Gaia explored very well. It's like we are going to release the data exactly at the same time for every single person in this planet, which I think is fantastic, and I think this is a great philosophy, and we really hope that we keep going in that way as we come from many decades of this proprietary data that has been always making big differences between the people who has more resources than the others. So I think releasing the data for everyone at the same time is a fantastic policy for science. We also offer, we have a strong connection with the virtual observatory facilities. We also offer, our catalogs are available in facilities like TopCat. So it's very easy. It's very well documented, and it's very easy to access. We just have to make the access to everyone as easy as possible, because what you want is that the data you are collecting, the data you are treating, okay, is just easy to use for everyone, and it's not extremely complicated, and everyone just gets lost because you want that people are using the data you are collecting. We have a beautiful interface where you just can navigate the image, and when you click in every single object you are interested, you can just get the spectrophotometer, and you just start to get the data. Because we use different photometric pipelines, we use different reduction pipelines, and different calibrations. You also have all the different facilities available are there, and it's just that it's just well documented, and you can just because every single science may require different kind of calibration. For example, for crowded areas, we need to use different pipelines than when you are on the field. So you can navigate these options to select what is the appropriate reduction or the appropriate photometric calibration, depending on the kind of science you want to do. And of course, you can contact us. We are always happy to help the people using our Havalambre data. Together with the big data releases, we also release valued added catalogs. So there are different groups working on very specific science. For example, there are people looking for emission line in galaxies. There are people looking for emission lines in binaries. So we try also to put together this information and release valued added catalog for the public. We are not only getting the data, calibrating the data, and releasing the data. We are also doing science in FEFCA. So this is just, I know I don't want to focus on the science, but I just want to mention that there different groups, like PhD students and postdocs and staff, just doing a wide variety of different science. So please, you remember the talks from Adrian, Sayali, Ale, Andres, and Jordi doing the cross-match between Gaia and J+. So, but what I want to focus here is mainly in the pipelines, in the archives, and the data public release, because I think that can be useful for Gaia NIR. Okay, so let me talk a little bit about the UPath, the unit for processing and archiving of the data. So I'm talking on behalf of Hector, that is the head of the UPath, because I'm not doing this at all, I'm doing science, so see how it goes. So what you get is just a beautiful table with the flags for a given wavelength, but when you are at the telescope, you just get this raw image. So from this raw image to the beautiful data that you are just using to do your science, there is a whole process, okay? So you need to sit down and develop your strategy, how you want to collect the data. Once the data starts to arrive, you have to storage the data, you have to reduce this data, and finally you also have to do your photometric calibration. So this is what the UPath is just doing in CEFCA. Okay? So the data is arriving from the telescope, okay? It goes to the headquarters in CEFCA, okay, and we use these facilities. So what I wanted to say is we have experienced years of developing all these pipelines, how to go, okay, collect the data acquisition, okay, the storage this data, treat this data, okay, develop the pipelines, and eventually calibrate photometrically all this data and releasing to the world. So I think this is pretty much what Gaia and Gaia NIR facilities are doing. So we believe we can be useful here. As I commented, we have our own pipelines, okay, to clean all the raw data and eventually just get what finally will be our science data, where we will eventually release to the public. One of the things also we have been paying attention is that you have to be extremely careful with your photometric calibration. This is work done by Carlos Lopez San Juan. He has been using a lot of white dwarf to see how well, especially from the photometry from Gaia, to see what are the random and the systematic errors that you can get when you are doing your photometric calibration. So we have experience treating all this data carefully, and we understand our systematics and our random errors, and also we have all the pipelines available as we keep collecting data and releasing the data. One of the big main goals of these surveys is it was motivated by cosmology, and we wanted to get photometric redshifts. Okay, that's the idea of using all these narrow bands. So this is our pipeline that has been developed by Hernán Caballero. All these data is public. So this is a comparison between the redshift photometric you are getting from a higher resolution spectra, much more expensive than photometry, and our photometric redshifts. So as commented, JPass has been motivated mainly to understand expansion and acceleration of the universe. So one of the main releases that we do is our photometric redshifts. And also, as commented, everything is public eventually, and we follow what we call these FAIR principles. It's just fundable, accessible, interpretable, and reusable. Okay, so I think this is kind of like same philosophy like Sloan Digital Sky Survey, same philosophy at Gaia, and I think is where astronomy is moving, just to make everything available for everyone in this planet at the same time. And also, just before I finish, I just want to emphasize that we are strongly connected to Arrakis. So we have a prototype of the camera being tested right now in Javalambre. That happens last year. And also we are developing CEFCA is leading one of the pipelines that it will be used by the mission Arrakis, called Harvester. So before I think this is my last slide, I just want to emphasize that I just wanted to promote what we are doing in Javalambre and in CEFCA, and I believe that that can be the beginning of a strong collaboration with Gaia NIR, as I think we have facilities that they can be interested for this mission. And of course, we will be grateful to host eventually the next Gaia NIR meeting in Teruel. Thank you so much for your attention.
Thank you. Questions for Borja?
Clear.
Everything very clear, indeed.
Oh, no.
There is a
Okay.
question.
Do you have any problem now? After many years, Javalambre, now everything is speeding up. So weather, climate change, lack of space, whatever.
You're talking about weather.
I'm talking about everything in general.
Things are going smoothly than previously. Okay, so we are.
That's what I see from.
We're in a good pace. We're in a good pace. Yeah. Okay. Well. Yes. Oh, sorry. I'm sorry. Yeah. Okay. Yeah, we're in a good pace now. Okay. J-Pass started slow. Okay. But I mean, we are not facing big problems right now. Yeah.
When is the first data release?
For J+ with the small telescope is already DR4. DR4 was out, and the early data release of J+ happened last year. So we are expecting very soon another data release with J+.
Next year, or will it be this year?
Yeah, probably next year. Yeah.
No more questions? I think not. Okay,
Okay.
so then let's thank
Well,
the
thank
speaker
you.
again. Thank you. So the next speaker is going to be Chloe Paudois, discussing the modeling of the Milky Way exoplanet population. So I think we need to stop sharing. No? No? Oh, no way.
Hi, so my name is Chloe Padua. I'm working at the University of Barcelona, and I'm going to present quickly so my research is focusing I'm interested on the exoplanet population, but from a galactic point of view, no? So, okay, it was just to say, okay, we know 6,000 exoplanets, but even if you sum up all the candidates for now, it's still a negligible number to compared to the what we expect, but we can't detect. And those exoplanets are, we know they suffer a strong observational bias, so also I guess you saw this a lot, but this is, so the mass and the radius compared to the orbital period, we see what we detect depends on the method we use, and also it's strongly, we are still missing information in a lot of region, no? So all the small planets are really underrepresented. We detect almost no exoplanets similar to the planet of our solar system. And especially we have almost no detection in higher orbital periods because it's hard to detect, no? But except for some imaging technique exoplanet, we don't have no information in this region. And another bias we have is more geographical bias, is almost all the exoplanets we detect are really close by to the sun. So with the exception of, we see up, it's the Kepler field of view, and in the center, so those are the imaging exoplanets. But the huge majority is really close by to us. So what I'm working on is we predict how is the exoplanet population in the entire galaxy, no? Because we want to know, well, if exoplanets form everywhere, if we have the same type of exoplanet, or if giant planets form more in some region or no. And the goal would be to also study how this has been influenced by the galactic evolution and the stellar migration, etc. But so for this, we need to simulate the exoplanet population, and the problem is usually the simulation of exoplanet is more like we simulate the protoplanetary disk, and after we simulate like with hydrodynamical simulation how the planet form, etc. And this is like really long, and it costs a lot, like computationally, and so we can't run it for a huge amount of stars when not at a galactic scale. So what we did is develop a code to simulate like quickly exoplanet around a large sample of stars. And so to do so, yeah, we take into account the stellar parameters, because we know there is a link between like probability to have a planet and the stellar properties. And we combine results from observation and the result from a lot of planetary formation models, so those protoplanetary disk simulation, etc. And the goal would be to be able to predict yields of future mission, and so when those missions would have results, we would be able to constrain like the model parameters we used. So yeah, first I will just quickly summarize like what we do in the simulation. But so we can use either stars directly from observation, so a list of target stars, or we can use stars from a galactic simulation. So we would like have more parameters. And the second step is, once we have all of those stars, to simulate planets. So this is where we have more model dependence that I will detail a bit. So the first parameters is the occurrence rate. So it's the probability for one star to host at least one planet of a given type. And for now, we consider it only depends on the mass and the metallicity of the stars, because we have models for those parameters, but it may also depend on other categories. And so once we know if a star harbors a planet of a certain type, we need to know how many of them do they host, no? So this is a multiplicity. And this is a like big, it's really uncertain now, because here it's a histogram of the detected exoplanets, and we see like most of them are like in single systems, while like some models say, like for example, a stellar mass star, they will, if they host a Earth-like planet, they will host like in mean like 5 to 6 Earth-like planets, and we don't really like see those systems. So now we have like for each star of our like sample, we know how many exoplanets they have of each category, and now we have to assign parameters to those planets. So parameters being usually mass and period. So again, the same plot. So as we lack information on all the zone, we did a broad approximation, combining so the observational data we have and simulate a result of simulation to like have an idea of what the Earth-like population could look like. And so now all of our planets have a mass, a period, etc. And so this is a quick result. So this is for a galactic simulation. We took like a region close to like equivalent to the solar neighborhood. And so we obtained like 23 million planets. And so you can see like this is a random sample of some systems. So you see we have a lot of like multiple systems. And the interesting thing is like half of the exoplanets we predict are Earth-like planets that we almost like don't see in real data. And so we can do this for different regions of this simulated galaxy. And we can see like, okay, by the mean number we have per system is 6 to 7 exoplanets. And we see, okay, if we move to the halo, so like metal poorer region, it go down, it's a 2 column on the right, we go down to 4 to 5 exoplanets. So yeah, and like the fraction of Earth like is always like really important, no? But the thing is, we can't check if it's real, because for now we don't reach those regions. So we need a way to check how like good or no is our model. And so to do so, we need to compare with observations. But so what we do, like we do it with Kepler because we already have the data. What we do is to reproduce the observational bias, basically, of one observer, apply it to our simulated population, and after we can compare what we obtain, no? And so, like, fix the model, basically. So for Kepler, we just took the target list of Kepler, we applied all of this process, and we obtained like 1.6 million exoplanets. After we assign them random inclination, and to reproduce observational bias, we don't reduce it, but we compute the signal-to-noise ratio that Kepler would have for those planets to know if they will detect them or no. So just, well, we have all the quantity necessary to compute the signal-to-noise ratio. And this is just, we checked, like, for real exoplanets detected by Kepler, we recalculated the signal-to-noise ratio to see how good we were at computing it, and so it's on the right. It's not exact because there are a lot of factors we don't take into account, but globally we recover the trend. And so those are the preliminary, well, the first iteration results, no? On the left, it's the mass and radius of the exoplanet we consider detectable by Kepler, and on the right, the real data. And the first thing, well, we have 10 times more detectable exoplanets, so we know there are something in the parameter in the models that are not well constrained, but the global trend is recovered. And so with this, now what we are doing is refining the input parameters, no? And like, we are using a similar technique that Sagar Malhotra described before to like try to infer the input parameter running the simulation like a million of times. And yeah, so we do it again, we will improve it. And once we have like refined parameters for the simulation, we would be able to apply it to other missions. Yeah, I forgot yesterday that Gaia NIR had a beautiful logo, so this is not a counter offer because I did it really quickly. But so yeah, we will predict the yields, and when we would have the real data, we will have even more information to refine like some, like the occurrence rate, multiplicity and stuff. And yeah, and once we have this, we will be able to have so accurate prediction also of how the population is in other places of the galaxy, you know, to know better the link between the stellar parameters and the presence of exoplanets or no. And I will finish with this. It's like a paper we went out like in December, I think, that they released a mock catalog of the exoplanet that would be detected, like published in Gaia NIR 4 and NIR 5. And so, well, the orange square is just to compare to the first plot, no, because the scale is quite different. But so it will be basically cold giants. And so if Gaia NIR would be, I guess, also only sensitive to like really big planets, no? But we would be able to have like, to fill up a bit the space like at larger periods. So I guess we have almost no knowledge about this, so it would be really interesting. And I went really fast, so if you have a question, that's it.
Questions?
Hi, I was wondering how do you deal with the observational biases? So like photometry is biased towards hot Jupiters, for example. So when you make your random generation of exoplanets, do you truly randomly generate these sets? I mean, or are you basing it on observational data that we have already?
You know, to know if there is a hot Jupiter
I mean,
or
we
no.
don't know the true distribution of exoplanet systems.
Yeah. No, like we use a occurrence rate function, no? Like what is the probability for a star to have a hot Jupiter or no? And so this is quite low actually, like in the models. So we like the probability to have a hot Jupiter. It's like, well, I have it, but it's so that yeah. So this is like depending on the mass and metallicity. The orange one is a fraction of stars that will host a Jupiter. So in the mod, sorry. Like even if they are like overrepresented in observation, the models say like they are not so common. No? So this is like taken into account, but also, well, there are different models, so we have to find which one is the most accurate. So this is why we are doing now.
Okay, thanks. Just a little comment on your logo, which is very nice at the end. Just for everybody as well, I mean, I've seen in this talk and in many others that people use different things for Gaia NIR. So many people have a Gaia gap NIR, and then other people have Gaia -NIR, and then other people have capitals all in Gaia. And so the correct one to use is as you have, but without the gap. That was the intended one. So if you could modify this, I would like a copy of it afterwards to use. Thanks.
Très bien, Chloe. In the break, please talk to me.
Okay.
I strongly encourage you to do this analysis in the southern pointing of plateau, starting in. Okay, done. Good.
Yeah.
Good. Publish it.
Okay, so if not, let's thank you again. Thank you. We resume at 11:20.
¿Están las charlas? La Laura que la hará online. ¿Esta es la tuya, Fede? Sí. Hay que dejar de compartir y... ¿Sí?
Sí.
Perfecto.
Ahí.
I give you a 5-minute warning, okay? Okay. So we will try to stick to that. Okay, welcome back everyone. Please take your seats. Let's try to stick to the schedule. Next talk is Friedrich Anders. He will talk about the future Roman Galactic Plane Survey and Hayden and synergies with Gaia NIR.
Okay, let's admit Pedro. Okay. Okay, I have 20 minutes. It's quite an impossible mission, but I'm going to try to comply with what Cesca ordered me to do. I'm going to tell you a bit about the Roman Galactic Plane Survey, which, let's just start with this slide, otherwise I'm not going to manage, which is about to be launched this year, if everything goes well. So the Roman Space Telescope is a 3-meter class telescope that's going to observe in the infrared. It's going to be a toy that can be used for all kinds of sciences. As you can see, it's already assembled, and the NASA team at the Goddard Space Flight Center think that it's possible to launch it this year and no later than the beginning of next year. So latest May 27, but probably in September this year. There's the first slot. And so there's a call open for general investigator proposals. So if you have a science proposal that you want to do with a 3-meter class telescope that observes in infrared, then you can still submit until March 17. Now, as you can see in this little diagram here, the number of cataloged sources as a function of year, basically, Roman is going to be even surpassing the LSST, Rubin data, and Gaia by, well, 1 order or 2 orders of magnitude. Still don't know exactly. So there are 3, I don't know, probably not all of you know this, there are going to be 3 major surveys to be conducted in the first 5 years of the Roman mission. One is this high latitude wide area survey. Another one is the galactic bulge time domain survey. So they're going to observe these fields in the galactic bulge every 12 minutes. And then there's also a high latitude time domain survey in these areas here. And as of last year, there's also the galactic plane survey, which is the first general astrophysics survey, as they call it. And so this is going to be the most interesting one for the planning of Gaia NIR, because it's going to be observing more or less in the footprint of VVV, but much deeper, of course, and from space, and covering a wider area of the galactic disk. So this is here overlaying the footprint of the galactic plane survey on an LSST footprint, and there's going to be a talk on LSST Rubin afterwards. So they estimate that the total number of sources in Roman galactic plane survey would be 20 million, so that is 10 times Gaia. And the data will become available in like 2 or 3 years. So be prepared for this. The filters of the Roman Space Telescope used for the galactic plane survey will be also similar to Gaia NIR. So you will have I'm going to come to that. But anyway, also the depth will be very similar if if Gaia NIR is going to be an L-class mission, then we have very similar limiting magnitudes because the telescope is also a similar size. So the galactic plane survey of Roman will have 4 bands, JHKS basically, plus an intermediate band between H and K. That's going to be centered at 1.84 microns. It's going to be 22 magnitudes deep, or 23. That's, well, probably 22. And they estimate about 20 billion sources in the galactic plane, which is a considerable fraction of the total number of stars in the Milky Way, right? So that's what you can see here in this little image. So we're going to observe all this part and probably down to the edge of the Milky Way disk for red clump stars at least. Then another feature of the survey will be that there are going to be 2 epochs. So it's not just single scans, it's going to be 2 scans of the inner disk. They are separated by about 2 years. So this allows you to get proper motions with a precision of 400 micro-arc seconds per year. So it's not comparable to Gaia, of course, but at least it will be will allow you to separate the foreground stars from the background stars, let's say. Okay, so you can only do rudimentary kinematic studies with Roman on the galactic scale, let's say. Now, there are some obvious synergies when you think of combining Roman and Gaia NIR. So Roman is of very similar size and resolution, has similar bands. Roman, well, I don't know if that's true still. It's slightly deeper. It's probably a similar depth. And so what you can do is to go for a joint astrometric solution, as in TIGAS, or Hipparchus plus Gaia, and as explained by David 2 days ago, when you can combine Gaia and Gaia NIR, you can, for the stars that don't have Gaia observations, because they're too faint in the optical, you can combine at least Gaia NIR and Roman. They're going to be like 20 years apart from each other. And so that allows you to bring down this proper motion precision by 1-2 orders of magnitude. So I don't know if this if this is all the right scale here, but more or less like this. Okay. And then there are some other possible science cases for you can look for long-term variables in the infrared. And of course, very interesting for Gaia NIR will be the Roman star counts that we can compare to simulations that Eduard has been telling you about before. And I'm sure there's going to be lots of other ideas for that. Okay. So in terms of schedule, as I told you, as of now, it's going to be complete, the Roman Galactic Plane Survey, complete in 2028, and that means that the data will be public probably by the end of 28 or 29, which is very good for us in Gaia NIR. All right. Then I'm going to come quickly to the second part of the talk. Now, when you want to make maps of the Milky Way, we know that in Gaia red clump stars, you can go down to up to 10 kiloparsecs from the galactic plane. OB stars, if you look at the maps, they end at 4 or 5 kiloparsecs from the sun. So as you go further away from the sun, of course, the distance accuracy becomes very important to make good maps. Now, how you can make maps more precise and more accurate is you combine your astrometric distances with photometry, with spectroscopy, and then you can determine better distances, extinction, and also ages. And as you've heard in the first day of the talk, first day of the conference, ages are of course super important when we want to age date the history of the Milky Way. So when you combine different sets of data, you can get a better handle on ages and break the degeneracy between ages and masses and metallicity, for example. Okay, now, as of today, the precision is quite good for this kind of experiments. So you can get ages for hundreds of thousands of stars, but not better than 20%. And if you look only at the best 1% of cases, for example, in this paper that is just about to come out, for the oldest stars in the Milky Way that give you also a limit on the age of the universe, the precision of age will be around 10%, but the accuracy is 15%. So you cannot go below 15%. Maybe depending on what kind of systematics you account for, it can be even 20 or 30%, the accuracy. And you saw that also in these star formation histories shown by Mark in the first, on the first day, that different groups obtain different star formation histories. This is because of the limited accuracy of our stellar models. So, why? Well, because we sweep most of the systematic uncertainties under the carpet. Now, if we look below the carpet, then we find lots of things that stellar astrophysics community knows, of course, about, but from the galactic point of view, we often forget about them. So equation of state, opacities, atmospheres, differential rotation of stars, angular momentum transport, chemical mixing inside stars, convection, helium abundances, magnetic fields, etc. Okay. So if you want to actually go to precision ages for lots of stars and not just accuracy, so we want to make the we want not just precision but also accuracy. So both accuracy and precision. We need Haydn, which is a proposal for an ESA M8 mission, for the ESA M8 mission, where Spain is heavily involved, and the Spanish community is being represented in the council by Andrés Moya and Juan Carlos Suarez from Granada. It was already an M7 proposal, so I have to tell you what Haydn means. It means high precision astroseismology in dense stellar fields. So it also has an obvious connection to Gaia NIR, because Haydn will do astroseismology as good as Kepler, but on a much smaller PSF. So you will see that we can advance our knowledge of the stellar physics ingredients, and this will have influences not just on stellar physics, but also on stellar populations, cosmology, exoplanets, gravitational waves, etc. So you can look at it like this, like David. If this was this was a slide that I stole from David, that he stole from the 90s. But with Haydn, which is just an M-class mission, you can do not all of what Gaia pretended to do, but at least some of the things, stellar physics, stellar systems, exoplanets, galactic structure, and maybe something related to fundamental physics. So the science objectives of the higher level science objective of the Haydn mission are precision stellar astrophysics, using star clusters as fundamental calibrators, and then galactic archaeology and also exoplanet systems. How is this going to be possible? Well, Haydn is going to be observing for around 4 or 5 years, and it's going to stare at specific interesting objects in the sky for a long time. So there's going to be, the prime object will be 47 TAC, where it will be observing for 18 months. Then we have M67 for 9 months, H and Chi Persei. I think that was an idea of Ignacio Negrela. for I think 6 months, and then my favorite object is here, Bades window, also 6 months. The idea is to use star clusters as fundamental calibrators, and we choose these star clusters to cover different ages, densities, and masses. And in the case of Bades window, this is the obvious place to look for in the optical, because it's a really, really complex mixture of stellar populations, and the density is super high. So with one shot, you can get 100,000 stars with astroseismology, okay? So this is the preliminary list of targets, the same as on the previous slide, and the type of science that you can do in each of the fields, okay? So this is from the M8 proposal. So we can constrain the mass loss, mixing processes in the stellar interiors, depending on how long and which objects we are looking at. So here's an example of how HAIDN is going to work. So we try to detect stellar oscillations in the extremely precise time series photometry. And this depends, of course, then on the magnitude, on the noise to signal ratio, basically. So we obtain very precise light curves. In this case, this is Kepler light curve, but HAIDN is going to be similar. Then we make a Fourier transform of these light curves, and we obtain information then on the granulation, on the star spots, so rotation. Then we can do, for the stars with rotation, you can do gyrochronology, and for the stars with solar-like oscillations here, you can infer not just the mass and radius, but also the core mass, density, internal structure, helium ionization zone, etc., depending on how well-defined this spectrum of solar-like oscillations is. Okay, so this is the timeline for the current timeline for HAIDN. So lots of things are going on in 2026 because we want to move to phase 2. Right now there are 10 candidates in the M8 slot, and it's going to be reduced to 5 soon. So let's hope HAIDN is going to make the cut. We are very well, I think, organized already, and as you can see, there's a lot of Spanish participation both in the industry and in the science. So to wrap up, HAIDN is a very interesting proposal for the next ESA M8 mission. We will produce high precision, long and uninterrupted photometric monitoring. And this allows us to go this step from precision to accuracy in stellar modeling. And it will have, as Gaia NIR and as Gaia, has an impact on many different branches of astrophysics. And Spain already has a very big participation in the project. If you are interested to also collaborate, then contact your local person at your institution, or Andy Moya in Valencia. Now, as for the synergies that I just made this slide in the morning that I can see from direct synergies between HAIDN and Gaia NIR. So if it is actually adopted, then HAIDN will be the benchmark for stellar models in the Gaia NIR era. So this will, of course, have a very good impact on the accuracy of any things that will be derived from Gaia NIR, so ages, as I tried to explain you, but also distances. So this will have an impact on the cosmic distance ladder also. Obviously, since HAIDN is observing star clusters, you can do a lot of star cluster science if you also co-observe in the infrared, and you have the kinematics from Gaia NIR there. And essentially, so I'm most interested in these ages here. So if you combine HAIDN, Gaia NIR, and the spectroscopic follow-up missions, then you can derive very precise ages for first hundreds of thousand stars, but actually if you then only use Haydn to calibrate together with Kepler and Plato, then you can probably derive good ages for millions of stars. And then we can rewrite the evolutionary history of the Milky Way. And I refer to Karma's talk for that. Okay, thanks.
No, I mean, I like this. I think it's a drawing you made here of the combined Gaia NIR and Roman plot, was it? From these curves you have at the start, but we could do a fairly precise.
Yes.
Yeah, we could do a fairly precise estimate actually of this, and I think we should do that and use it as a selling point for Gaia NIR, because I think we will get down to a few micro-arc seconds per year. For the combined solutions, and also the same for LSST. We can also do this calculation. And even though it's optical, but it's still useful to show people. Thanks. You can see, do you have the data for those curves, or a reference to them at least? I need the exact numbers.
Okay, can do that. Yeah.
Friedrich, can you please remind us the name of the competitors for M8 of
there are 9 competitors. I remember the ones for M7, but they're...
But how many competitors are there in...
So there's no stellar evolution, like no stellar science competitor. In this respect, Haydn is alone, but there are different sciences. There's cosmology, there's small X-ray mission, I believe, planetary science, so it's all kinds of science.
No? No sé si... Ah, ya está abierta.
Es más fácil así, no lo han hecho, estaban. ¿Esto de quién es?
Eso es.
Venga, vamos a...
Tenemos que compartir.
Vamos aquí.
Okay. So our next speaker is Eduardo Martin, and he will talk about Euclid and its relation and impact on Gaia NIR.
Thank you to the organizers for having me here. And I would like to present on Euclid. This is an ESA-led mission that was launched in July 2023 and is successfully getting data, as I will show you in a moment. So I hope I press the right keyboard here, the right key. The PI of Euclid sadly passed away less than 2 months ago, Yannick Melier. So I just put this in memory of him. And this reminds us that space missions are really a long endeavor, and particularly Gaia NIR infrared is poised to be in the midterm. So main paper that came out describing the Euclid mission appeared in a special volume of Astronomy and Astrophysics named Euclid on Sky. This is a tour de force paper with 94 pages and more than 1,000 co-authors, and already has received 655 citations. That's a picture of the Euclid launch. ESA had a special place for the people who were involved in the mission and came to Cabo Cañaveral. The mission was supposed to launch from Kourou, but because of the Ukrainian-Russian war, it was canceled. The spacecraft, the Russian launcher, and finally it was launched by SpaceX. That's also Euclid when it was finally assembled, and it's a 1.2 meter wide area telescope. It has two instruments, a visible imager with high spatial resolution and just one passband, and a near-infrared instrument with 3 passbands and slitless low-resolution spectroscopy. These are the Euclid passbands from Yannick Mellier paper. And you can see here the wide passband compared with Gaia, and the wide near-infrared passbands that include the telluric absorption. So it's a special system, but it's well calibrated. The depth of the Euclid was published in Jean-Charles Couillon's paper, and at 5 sigma, 4 stars, it reached 27th magnitude. This is in the AB system, okay? And in the near-infrared is around 24.5 for the 3 passbands. But when we actually want to select point sources, the limits become shallower because we have to reject a lot of things. And then here you can see the detection limits, but then when we apply filtering to get really good quality point sources, then we are about 1.5 magnitudes shallower than those limits to get really good parameters. The spectroscopy is quite good, up to about a magnitude of 18.5. We're pushing it to 19. Here you can see an example of a T-type substellar object with the main absorption features. So this is basically here we can see the water band that is hard to observe from the Earth, and also methane. A number of T-dwarfs, new T-dwarfs were reported in the first quick release in this paper by Carlos Dominguez Taglia and collaborators. And now, Marusa Serhal and collaborators are working on the full exploitation of the Q1 release and also the internal release of the DR1. And Here you can see a color diagram, and this is particularly focusing in the region where the ultra-cool dwarfs of the coolest temperatures are expected. A few of them already have spectroscopy by the Euclid system, but most of them are still not characterized spectroscopically. About 1,000 have spectra, and there are about 1 million of candidates. Euclid has a field of view larger than the full moon. It has a lot of detectors, detector mosaic, high quality detectors. Initially, it made a program that was an internal competition inside the Euclid collaboration, and it was called the Early Release Observation Program. It was the first public data release. And here the collaboration proposed different type of systems, some of them outside the main Euclid surveys. Today I will tell you a little bit about these green ones that are outside the Euclid survey. They are in the galactic plane, and they correspond to nearby star-forming regions and jump-on clusters. But, well, there are other interesting targets that you can recognize. The imaging and photometric and astrometric catalogs are public. The spectroscopy is not public. We're still working on it. And this is the wide survey that is underway now, and there will be the first release in the about October, we expect, October this year. In this release, there will be about 2,000 square degrees. And before that, there was the quick release with only one pass of the deep fields. So you can see the deep fields here, the south one, the north one, and there is another one. This is the timeline. The main mission will last for 6 years. There is the possibility of an extension. We already had the Q1 data release, and then there is coming the data release number 1. Then there will be the quick release number 2, and that will be a special one because that is going to be not part of the main surveys, but a galactic center microlensing survey, so it's quite special. Then there is the general data release number 2, that is going to be with a larger area and more data products than the data release number 1. The quick releases 3 and 4 are undecided yet. There will be an internal call for proposals for the Euclid collaboration to see. Right now we're gathering ideas, and we still don't know, but they have to be kept because when the mission was adopted, there is a commitment to do them. And then the data release number 3. So this is where we are now with the dates. So we recently had the internal data release number 1. Not complete, but we already have a lot of data to work on. And in March, we expect the full internal data release, which will become public in October. And, well, that's the schedule. You will have that together with the other presentations. Now I'm coming to the more specific part of the presentation, the talk, that this is about ultra-cool dwarf science. Here this is coming from a proposal to the ERC, and it's based on some picture that was I took from Karma Gallard and modified for ultra-cool dwarfs. So here you have the Gaia completeness limit for the latest M-type dwarfs, and that's about 100 parsec. So in this picture is this tiny circle here. Then for the same spectral type, the white survey will get to 1.7 kilos parsec. So it's this circle here. And then the deep surveys will get to almost 2 kiloparsecs. So you can see the big advantage of that. That's for the extragalactic sky. The ERO program explore what Euclid can do for nearby star-forming regions, this is a showcase of something that could happen, but we don't know for sure it will happen. This is something that we hope will happen, that Euclid covers larger areas of the nearby star-forming regions. In particular, this is Orion. In one single shot, you can see Euclid covers a small part, but is representative of what we can get. In particular, for this Euclid on Sky special issue, we focus on half of one shot of Euclid, because it was the one that is simpler and better studied. We had been studying the Sigma Orionis open cluster for many years. Some people here, like Jose Caballero, know that very well, that at the IC we are studying this particular open cluster because it's an open cluster where the massive stars have cleared a region and is quite free of interstellar extinction. And then there is a shock front that you can see here, very clear, very nicely defined with the sharp Euclid images. And then after that is the mess. So first we started with the clean part, with the low reddening, and now we're working on the high reddening part. It's much harder. So there are some very famous features here, like the Horsehead Nebula in this region. So for the clean part, what we did was to check on the objects that we had been studying for many years using the GTC, the VLT, and some of them we had to reject, and some of them were confirmed. And then we added a few more, but not up to the limit of Euclid, because then there was too much confusion. So we stayed in a relatively safe part. So we were able to extend it to below 4 Jupiter mass and find a few more candidates and define a nice sequence that compares quite well with the 3 million year isochron for the distance of the cluster. This is the color magnitude of that region. You can again see that the part covered by the substellar objects is quite clean and free of contamination, but for comparison, this is the other half. And here you can see that it's a lot more messy. This is sharp images from Euclid. We were able to find, by direct imaging, one candidate companion to a planetary mass object in the cluster. This is still to be confirmed. and we derive, combining Gaia and Euclid, the mass function. There is little overlap between Gaia and Euclid, because when Gaia stops, Euclid is almost saturated. So, but it's about half a magnitude good overlap only, but still it's very useful to combine both to get the mass function, in particular in this region. Of course, when we have Gaia near infrared, this will become more solid, because then we can extend that with a better overlap with Euclid. Another region that we studied was the Taurus star-forming region, again, a small but representative part. And here, this is a recent paper led by Hervé Bouy, and we can get down to about 2 Jupiter mass. And for this region, we have some proper motion information compared with ground-based data. We were able to use that to further clean the sample. In conclusion, what I have to tell you is that I really think there is a good match, not perfect, but good match between Euclid that is providing deep imaging and reconnaissance spectroscopy and what is expected from the Gaia NIR infrared, providing the very, very fundamental and necessary proper motions of parallaxes to assess the membership into the different regions and to further identify and characterize the nature of the substellar objects, ultra-cool dwarfs. That's very promising, and well, I hope to stay to see that from the retirement. Thank you.
Yeah, so I was wondering about the positional and proper motion uncertainties, because you can do relative astrometry with the images you get from Euclid as well. Is somebody working on that, and are those numbers available anywhere? Because we could then combine those with Gaia NIR and actually get improved proper motions, basically, with a long time baseline.
The internal astrometric precision is published. I know one paper on a globular cluster. I can send you the reference. And there is also, for this paper in Taurus, it's also published there. In particular for Taurus, it's a lower density region.
Yes.
But yes, we have some numbers, and I can share that.
Yeah, it would be very useful to estimate what we can do. Thanks.
Sure. And we will get additional information for the Euclid deep fields, because the Euclid deep field have several passes, and usually they are observed about once every month. So for those fields, we will get better estimates for the general fields of stars without any cluster.
Ya está.
Hola, Laura.
Hola. Comparto la pantalla, ¿no?
Sí.
So it's Laura Toribio. She will talk about the Rubin telescope and the LSST survey and the relation to Gaia NIR infrared.
Could you see my screen?
Yes.
Yes, give me a moment because now I don't see you. Where are you? Where is the... Okay. And I have to put on... No. Sorry. Now?
Yes.
Okay. Thanks to the organizer to inviting me to give this talk and also for allowing me to give online for all the problems that the last week. So, well, my name is Laura Toribio. I work at the CIEMAT at Madrid, and during the last 2 years, I was working in the commissioning of the Vera Rubin Observatory. So today, I would like to show you this observatory and the different I have to another ones, and also to talk about the possible synergies with the Gaia NIR. So the observatory is an initiative of US, is funded for US National Science Foundation and also for US Department of Energy, but is located at Chile, at Cerro Pachón. The location is a very good place to observe the sky since of there. No, it's a ground-based initiative. Oh, come on. Well, that okay. It's an initiative, ground-based observatory. At very near, you can see another observatories like the Gemini telescope of the SOAR telescope. So before to start, I would clarify some terms that I know are a few confused in the literature, because the official name of the observatory is Vera Rubin Observatory. The original name was LSST Observatory, and the acronym was Large Synergy Survey Telescope. But when Vera Rubin died, they decided to change the name to Vera Rubin Observatory. But they want to conserve the name of LSST, so they decide to call the survey LSST, and the acronym is Legacy Survey of Space and Time. And the telescope they called Simonyi Survey Telescope. And sometimes we confuse and we make a mess of this terminology, but more or less we talk about the same. So the Simonyi telescope is a few different to other telescopes. The primary mirror has 8.4 meter of diameter, but the effective part is 6.5 meter effective. And this is because in the primary mirror there are a hole where is located the tertiary mirror. I want to show you. So in a normal telescope, the light arrives to the universe, to our primary mirror, and then the light go to the secondary mirror and then to the camera. But here is a few different. The light arrives to the primary mirror, then go to the secondary mirror, and then go to a tertiary mirror that is located inside to the primary mirror in a secondary curvature. Here, and then go to the camera that is in this part. Here you can see this picture when they are polishing the primary mirror, and it's very easy to see in this brown part the tertiary mirror. This is the secondary curvature that has the main mirror of the telescope. So also, the camera is very special because it's the biggest cameras of the world. The field of view is around 9.6 square degrees, and we have 6 different filters that cover the ultraviolet, optical, and a part of the near infrared. The idea of this telescope is that it's very compact, so it can move very fast, and the field of view is very big. So we can scan, observe the totally of the sky more or less around 3 days. So the telescope starts to take data of the sky, and in 3 days more or less start again. So you have like a feel of the sky, and you have to see any change of the sky, like supernova explosion, variable star, binary mirror. So here more details of the camera. More or less the site is like a car, and the field of view is around 45 times the area of the full moons that you can see here. More or less the idea of the size of the camera, and here you can see the cis filter that cover this ultraviolet to near infrared. Is near infrared, but not like Gaia NIR, of course. Now, then we see better this point of view. So the idea is this, that the telescope take data of the sky during 10 years, and around 3 days, start again to see the sky. So at the final of these 10 years, we expect to have a very complete survey of the south, of the sky of the south, and the depth will be more or less 27.5. And also we will have a feel on how the sky changed during these 10 years. So this is a pictures of the telescope, and you can see better the site, because here there are a lot of people, and more or less you can see the camera is in. No, in this picture don't see the camera. And here, when it's myself with Nacho Sevilla, this last summer, then we was in Chile working in the commissioning. So this month, in January, the LSST began to collecting the data. So we are very happy because LSST is a reality, and after all this past year working, we are taking data of the sky. So the idea is that the telescope take information and measure million of galaxy, star, and only transit per night. Here I put 2 pictures to see the difference that we expect to have with data with other service like Sloan, and we expect to have more or less this with the LSST. So the data will take with short exposure, the 30 seconds in the 6 different bands, and we expect to cover the 18,000 square degrees, the south of the sky, and we will have a very big volume of the data per night. So something that I think is very important is to know that the alerts will be public. And what is the alert? When the telescope detects a change between one picture and the picture that take 3 days later, the telescope sent an alert. And this change could be, for example, supernova explosion, can to be comet, asteroids, binary stars, variable stars. So if some of you works in some of this field and can to be interesting for you, knows that in probably very early, the telescope start to be public all this information for you. So this is important. The telescope starts this month to take data. In more or less 1 year, we hope to have the first data release, but the first data release the first people that see this information is the collaboration, the people in the collaboration. So in 2 years, will be published for all the scientific community the first data release of the data. And then we expect to publish one data release more each years. No? And the final total, we will have 10 data release. And what I said before, the alert are public immediately. So I think this is very interesting. And I was thinking during the last 2 days, during the talk, and I think the Vera Rubin doesn't detect exoplanet transit. Maybe with this kind of variation of the sky, it's not possible to detect. But I am not sure. Maybe for the people that work in exoplanet, maybe can to be also interesting to see this information. And the data release provide photometric, astrometric, photometric receive information, property of the different object, this kind of thing that inside to the collaboration we can to give for the rest of the scientists. So this is the 4 main areas of the telescope. I think the telescope board thinking in dark matter and energy matter probably is the less interesting for the community in this meeting, but I think the part of to study the Milky Way structure and formation is very interesting for you. Also the solar system, because here the idea is to have a new census of the new asteroids and comets that the telescope detect for this difference between the sky, between one data and the data that takes some days after, and also to detect changes in the sky like supernova explosion or this kind of object. So now I want to talk a few about the synergy with Gaia NIR. I have to say that after to listen you these last 2 days, and because many of you work in a specific science and give a lot of details about the improvement with Gaia NIR, I think is not my point of view in this talk because it's more generic. And yesterday someone said that LSST was a competition of Gaia NIR, and really I think is a very it's not a competition. They can to work together very good and to complement it very good. So something new, because all people talk about this. One of the before to say the difference and the capacity of both mission. LSST is a ground base, and the idea is to have a wide 5 survey. However, the Gaia is a space base, and the idea is to have a very good astrometry mission. So one important thing is the operational time. If you see, don't overlap on time. The LSST start now and finish it in 10 years, and probably Gaia NIR is later than this time for the LSST. The primary goal of LSST is to have a very good survey, deep, and to see this change around the time. And the Gaia NIR is to have high precision in astrometry using the near infrared information. The range of the wavelength also is different because LSST is more focused in the optical and the very, very near infrared, and Gaia NIR in infrared. The filters, in LSST we have 6 filters. In Gaia NIR I don't find information. I didn't find information about that, but probably it's me that I don't find it. LSST cover the south sky because it's a ground base located in Chile, and Gaia NIR all the sky. And the deep that we have to have in the LSST after 10 years is around 27.5. And the Gaia NIR, sorry, because I didn't find information, maybe because I am a person that I don't know to find this information. So I think it's important to know that it's true that the timelines don't have overlap, but it's not important because they provide a complementary view of the sky in optical and also in infrared. So here you can see the idea of the wavelength that they cover, and I think it's very important to see this part that is a small part with overlap because they allow to make the cross calibration on the future. So I think they are a very good complementary wavelength regimens to make science. So nothing new about here because all the people talk about this, but one of synergy can to be to use the information of Gaia to study the dust oscuration region of the galactic structure, because LSST can to provide very good photometry and to detect a lot of different objects, but the stellar extinction is very important when we are observing the sky from the Earth. So I think Gaia NIR can to provide a very good astrometry, and currently LSST use the information of the Gaia, no Gaia NIR, the Gaia for make the astrometry. So having this information in infrared, I think will be a very good improvement of the data. And also very similar to study the stellar population, because LSST will provide deep multiple band optical photometry for billions of stars, but in the part where there are much dust, it's impossible and LSST can't see anything. So I think it's very important the part of the near infrared. The last synergy that I put here, because it's more, yes, it's more or less, is the part of the variable star and transit in galactic context, because LSST see where there are a variation of the sky and say, here there are a variable star, here there are a transit, and this kind of thing, but not focus into a study that, because the goal of the LSST is other. So I think other mission, other telescope can to use this information, or where are the variable star, where are the transit, to study with more detail and more precision. So Gaia NIR had to provide this near-infrared astrometry for all these new objects that LSST will be detected. So this is my talk. Thank you so much. If you have any questions, I am here.
Hola, Laura. Alessandro here.
Hola, Alessandro.
I'd like to make a couple of comments and then ask you a question. Insisting on what you said of using the proper names, a reminder to everyone that writing VRO as an abbreviation for Vera Rubin Observatory is highly discouraged. Laura, you didn't use it, but I think it was important to mention it.
No, but they don't want that we use this. They don't want that. Yeah, it's important to say. Yeah, it's true. They want that we use Vera Rubin Observatory or Rubin Observatory or Rubin, but no VRO.
And probably it's important in this context to comment also that the mount of the telescope was actually built in Spain, and that was one of the two fundamental subsystems, because the telescope had a very important requirement on the movement, and that was crucial. The question I wanted to ask you is, because you've been involved in the commissioning, and I think it was yesterday we were commenting on focusing on the most difficult part of a survey. So you probably pointed at the galactic plane with the Vera Rubin, with the Simoni telescope. So can you comment on how many stars are there in the galactic plane when you observe with an 8-meter telescope with a 5 square degrees field of view, and how does the pipeline work if the pipeline dies while looking at too many stars? Can you comment on something?
I am not sure if I can to comment something of that, because my work on the commissioning was focusing the mirror and the security of the mirror, the stability of the mirror. So I am not sure the pipeline and how they solve the problem of the galactic center. I think I'm sorry because I can't give you an answer.
Okay. Thanks. The mirror, by the way, is a fantastic piece of hardware.
Thanks.
Yes, Andres.
Hi, Laura. This is Andres Del Pino. Very nice to see you, even if it is online. I'm kind of curious about this 3-mirror design. Could you comment on that? What are the advantages of having 3 mirrors?
Yeah, the idea of to have 3 mirrors is because the field of view is bigger, and also you can make a more compact telescope and move it faster. This is the 2 reasons that they decide to make this new technology or this new design.
Questions? So let's thank Laura again. Thank you very much. We come to the final talk. This is Jose Caballero. He will talk about Habitable World Observatory and Large Interferometer for Exoplanets. Just learned that. And Tianlin. You will hear that. Possible competition, at least the life, right? For Gaia NIR.
What is this? Unmute?
Stop sharing. Ah, no. Oh, Laura, can you? No. Laura needs to stop sharing, please.
Yeah, I stopped sharing, no? No. Sorry.
Now.
Sorry, Jose.
En el navegador.
En esto, en Chrome.
Caballero. Ahí.
Sí, y primero
pantalla
compartir.
completa. Hola y saludos a todos. Thank you very much. Not this one. Thank you. Thank you to the organizers. In the schedule, it is written HWO on live. Rainer, vielen Dank. It is a Habitable Worlds Observatory and Large Interferometer for Exoplanets. And the first slide will be...
No, porque es el navegador.
Es un Mac. Creo que dicen estas de acá. Aquí. Ahí. Ah, no.
Lo tengo. Modo presentación. Venga.
Venga, que ya terminamos. Habitable Worlds Observatory and Large Interferometer for Exoplanets. So I will start from the end. This is what we want. This is what HWO and Life wants. An image of an Earth twin. One Earth mass, one Earth radius at one astronomical unit to a G2 5 star. This would be actually close to the reality. Left, spectra in the optical, from the ultraviolet to the near infrared, and to the right is in the mid-infrared. Optical to the left would be HWO,
The right would be live. This is the simulations. This would be the reality after exposing for something like a few days on those stars, and how we can manage it. Then we have to start from the beginning. And the beginning is actually May 2021. It was the publication of the final recommendation from the Voyage 2050 Senior Committee. And I will read it. From the three themes, from temperate exoplanets to the Milky Way, the one in the middle, the other are solar system, and the other the outside the Milky Way, the Senior Committee considers a mission on the characterization of temperate exoplanets to have a higher scientific priority, that is, large interferometer for exoplanets. Should it be determined that this is not feasible, the Senior Committee recommends rather a focus on the galactic ecosystem with astrometry in the near infrared. That is Gaia NIR. Okay? We have the context about this. Isabel mentioned Habitable Worlds Observatory, that Spain must be there on the first day. And I just mentioned this thing. This is what it is written, but I will explain next. In the report of the Voyage 2050, there is also a room for European contribution to a next great observatory of NASA. This slide is very important. This is not exactly the one that Cecilia and Isabel showed, because this is the version just before the interministerial. This is the one that I have. The only difference is that the increase at the beginning, the slope is not 4.5%, it is actually 3.5%. And I want you to look at the L5 banana. That means an L5 study start around 2028, 2029, and adoption in 2039. Why I'm so sure that Gaia NIR will not be L4? Because L4 will go to Enceladus. Make it clear. Read your notes in classes, Enceladus, astrobiology interest, this stuff. So we have the L5 banana, and at the bottom there is a blue line. It is a pity, but it looks like a high-velocity train. That is NASA participation. So took these pieces of the ESA budget for the future. Now, what is LIFE, which is in principle what the Senior Committee proposed to be the first priority for L4? This is the summary slide. Basically, is 4 telescopes of 2 to 2.5 meters, separated by about 100 meters, and there is a 5th spacecraft, which is the collector, and that will make nulling interferometry, and will work from about 6 microns to 20 microns. And there is a huge challenge in flying formation and as well on detectors. And some of you would say, that looks like familiar to me, this thing of 4 spacecraft plus the collector. Those of you who are as old as me will recognize Darwin and the Terrestrial Planet Finder interferometer at the beginning of the 2000s and even the late of the 90s. So in 26 years, we have not improved too much on this. LIFE wants to do this. This is a real simulation of the solar system observed at 10 parsecs. And there you can see Earth, Venus, Jupiter, and even you can start seeing something of Mars. LIFE is having meetings as well as Gaia NIR. The last one was in Barcelona in November. And I was impressed by the results of Proba 3. It is doing heliophysics. It's making an artificial eclipse with a formation flying of only 2 telescopes. The requirement was having a precision in the relative position between the 2 units of 4.9 millimeters, separated 150 meters. But what we were told in Barcelona is that the actual measurements is 1 order of magnitude better than this. The Japanese are proposing another flying formation mission that will increase even 1 order of magnitude more, and that will be close to the requirements of LIFE. LIFE, Large Interferometer for Exoplanets, but what is HWO? First, let's go to a vintage image. These are the NASA Great Observatories: Compton Gamma Ray Observatory, Chandra, Hubble Space Telescope, SIRTIF, S-I-R-T-F, Spitzer. That is the original name of a Spitzer in the 90s. These were the 4 original NASA Great Observatories. Afterwards, it was James Webb. Before launch, NASA started thinking of what would be the NASA Great Observatory. And there were 4 proposals. There were LUVOIR, Large Ultraviolet Optical Infrared Telescope, HABEX, Habitable Exoplanets, Origins, which could be a Super Hubble, and LYNX, which could be a Super Chandra for X-rays. And they were supposed to be flying in the mid-2030s. Eventually, NASA made a selection and merged the proposals for LUVOIR and HABEX, which is Habitable Worlds Observatory, and which could be launched in mid-2040s. And this is the second architecture design of HWO. These are a couple of official slides from NASA. What is Habitable Worlds Observatory, Super Hubble, blah, blah, blah. Look at what it is written at the bottom. International contributions missions to be considered. Actually, NASA is actively in communication with ESA, Canadian Space Agency, and JAXA regarding potential contributions of other countries and agencies to HWO. And eventually, this does thing of finding biomarkers on the atmospheres of exoplanets. HWO, there are between 6 and 8 meters the primary mirror of axis. It will have, in principle, 4 instruments: a coronagraph, a high-resolution imager, and a multi-object spectrograph in the ultraviolet, and a 4th instrument to be defined, which could be POLUX, spectropolarimeter ultraviolet, that it is led by institutions in Europe. And for 2 years, until November last year, there was a huge international collaboration for defining the requirements for HWO, and also starting working on actual designs. There was something like 1,200 people working together, separated in science groups, technology, and community. And in particular, in my case, I was involved in the ones in white here, and I was in charge of some of the sub-packages. So that means that NASA allowed Europeans to be deeply involved in the scientific part of HWO. Of course, you know, you can say, no, but Donald Trump has said that there will be no budget and so on. NASA goes on working on different conceptual architectures. These are number 3, 4, and 5, and they are working on their conceptual architecture 6, which will be derived in a couple of months.
here something is missing. It's just to see the telescopes and the off-axis mirrors, but there will be a cover and plegable, ¿cómo se dice plegable? Foldable, a foldable tube that will cover the optical train to avoid collision by micrometeorites. Just news of 20 days ago, NASA has put 150 million euros for 7 companies, and there you can see the names, BAEM, L3Harris, Lockheed Martin, Northrop Grumman, for developing the design of HWO. So HWO is alive, well alive. And actually, the next HWO international meeting will be in Europe, will be in France, in December, in the south, close to Paris-Meudon. November 20th, December 4th, if some of you want to go. And personally, I am actively working on this thing of HWO, working on the science preparation, in particular on the target list. This is a published paper. The one is on AstroPH, and the third is about to be submitted, and there will be more, is for defining the target sample. And actually, I'm also involved in the target sample of the Large Interferometer for Exoplanets. So I said, why not joining forces? And then we said, okay, let's join forces. And besides, I said, okay, why not joining forces also with the Chinese Tianlin? Live HWO and Tianlin could join forces for the definition of the target samples because there will be stars at less than 20 parsecs or so. Tianlin may be earlier than HWO and LIVE. It will be a 6-meter telescope, 6.6, wavelength coverage from the ultraviolet to the H-band. On L2, Os-axis with 3 main instruments, and to be launched between 2035 and 2040. And you know the Chinese. If they say something, they do it. And that's all. Thank you very much. David first.
Yeah, so I will say only nice things. Your last slide was very interesting about the collaboration with China, because with Gaia NIR, as Frederick told us the other day, we may have to consider going to become a M-class mission if the money doesn't appear, even though our costs are really at the L class. And one solution for that kind of problem is that we would join forces with the Chinese and invite them into Gaia NIR also. But the other question is about habitable worlds and the LIFE mission. I mean, ESA can fulfill its requirements for temperate exoplanets by being involved in habitable worlds, basically. And at the moment, that's the way I see things going, because the LIFE mission will probably be just too expensive for an L-class mission even. So this is how I see things going. So we have 2 questions. How will Europe fulfill its what's it called, temperate exoplanet requirement, which gets priority, and then how also then Gaia NIR can become a large mission. So we have to find maybe more money, but I think there is a way forward for all of them, actually. So I'm kind of optimistic.
Regarding the Chinese collaboration, fully agree. Regarding the second, I will tell you later because I am recorded. But the answer is this, is L5. There is only money for one mission. And you know which is the mission that it is more prepared for the technology. Should it be determined that this is not feasible, this feasibility is what we are talking about. Microphone for you.
I'm just curious, just curiosity on the trade-off versus optical observations versus mid-infrared. So life is clearly mid-infrared and the rest of the observatories are optical. So could you comment on the trade-offs?
Sure. Remember that what we all, I'm also in Gaia NIR, but I'm interested in science. What we want is to see biomarkers on the atmospheres of exoplanets. It's not just measuring the composition of the atmospheres of planets. So we want robust identification of biomarkers. There is a number of biomarkers. There are some molecules, water, methane, CO2, that are only detected in the mid-infrared, and that there are others, ozone, the red leak, the photosynthetic effects that are only visible in the visual part. So I would say that eventually the two missions will be flying, maybe 2050. But we need both to have a robust claiming that we have detected life on another planet. We must avoid what we are watching in the news recently about we have detected phosphine, we have detected dimethyl, blah, blah, blah. And the only way is having a huge wavelength coverage and detecting a combination of biomarkers at different wavelengths.
This is an interesting end to talks. So thank you very much again.
Okay, so we're done. We made it. I think we have to congratulate everybody here and participating to this meeting. The goal of this workshop was to engage the Spanish scientific and industrial community, and I think that this has been a success. We can see the picture here of all the people that we were here in yesterday afternoon, plus the amount of people online. So we've been like more than 100 people participating to this meeting. So I think, and before talking with David Hobbs, that he's got a lot of ideas and a lot of projects and a lot of scientific cases. And so I think it's been very productive. Just to show you, I'm not going to read it, but this is my notes. So these are from only the scientific challenges. I think we have identified very different lines of research that Gaia NIR, or that would benefit from a Gaia NIR-like mission. Don't worry, we'll put this in the webpage. We have not only identifying research lines, but also identifying tools that could be useful. So the simulations, different kinds of simulations, cosmological, Milky Way-like simulations, mock catalog tools that we have seen that for Gaia have been useful and that we can extend to a Gaia NIR-like mission. Also, we have seen this very interesting session on synergies with other missions. So I think that for me, from my side, this is a very successful and productive meeting, not only from the scientific challenges or identifying scientific challenges, but also the technological science. So one of the questions we had yesterday after the roundtable with the industry is, okay, we have seen from David talk that the detectors seem to work, but what's the next challenge? So, okay, they work in the small modules. So, but the challenge is to combine them and have a larger module. So that could be the next technological challenge. From the instrument point of view, onboard data handling, on-ground data processing, so we have the lessons learned from Gaia and how we want to proceed. I think this is quite identified. And we had this, because we have been talking about it several times these days, we had a technological workshop last July in Cambridge, I think. From these conversations to these couple of days, we could have another one next year, something similar to the one we had in Cambridge, but maybe this time here in Spain. Jose was proposing a Coruña. Maybe finally we can go to La Coruña, Minia. Or as Fernando Buitrago was proposing before, to Teruel. So I think that the community has responded very, very well, so more than we could expect for the number of participants and the exchange of ideas and the challenges. So I'm closing here the meeting. Thank you very much, everybody, for coming and participating. And I think we will see each other very, very soon talking about Gaia NIR. So thank you very much to all. Thank you, everybody online as well. I hope it has worked. So the experience it's been a challenge as well, having this kind of hybrid workshop. But any feedback will be very well received. So have a good trip back home and see you soon.
Certificates next week by email.